So here I'm gonna show how I made the controls in VR especially. As we can see, I'm using hand tracking, and so this is a simple throttle. It's the model. It has this pivot point here. So a vector I'm calculating. This is grabbable. This is grabbable. It has a grabbable collider all around it, and this is my hand, which is like grabber. Let's say it's a grabbable, it's the grabber, and this is the pivot here because this handle will rotate on this axis. This is x-axis, so this handle will rotate based on this x-axis. So first I'm calculating a vector from grabbable to pivot. So this is the vector, and then I'm calculating the vector from grabber to pivot. So when I will grab this grabbable, and then this calculation will be done. So suppose I grabbed it and then I pulled my hand this much. So now we can see that this vector and this vector creates an angle, and this angle is what will tell this grabbable's visual, this handle, to move itself towards this grabber. So now we'll pull. There will be two vectors, one from pivot to grabber, one from pivot to grabbable, and when I will pull my hand in any direction, then it will only calculate what is happening, what is the angle in this plane. So if I grab it and then I push it and it's moving, if I pull it, I see it's moving. So this distance is actually interpolated, so it feels like a smooth moving rather than a jittery. And when I'm pushing it, the spaceship is moving forward. When I'm pulling it, the spaceship is moving backward. Yeah, and when I will release it, it will go back to its original position just for a damping. We can definitely tweak this the way we want. Like we can make a snap point in the center, or we can just make the lerping value faster so it feels like it coming with the hand. Just made it for smooth aesthetics. But anyway, this is customizable. What's about the control handle? It's also quite similar, but here rather than using a single vector and rotation on a basis of a single angle, a single axis, here we are actually moving in different axes. So first is this yaw movement, yaw rotation, which is if I grab it and then I push it, we can see the spaceship is rotating on its y-axis. If I rotate it this way, we can see the same. And then there is this pitch. If I push it this way, it's pitching, and if I pull it back, you can see that it's pitching back. So, and that radar is telling which is the z-axis of the entire world. It's like the z-axis of unit is seen. So that spaceship, when it will actually be like this, so there we go. Now we are kind of quite pointing towards z-axis. Yeah, so that's the z direction. And now, so what's the maths here is same grabber's vector and grabbable's vector, but we can see, yeah, and also the handle is rotating quite similarly. As we can see, the handle is also rotating, and it has a constraint angle, so it doesn't rotate too much. We will see in the code and it will be more clearer. But yeah, this is the basic principle of these controls. So now we are back to our project, and this is the persistent player that gets spawned from network manager, and this script will spawn the player avatar depending on the avatar we chose. And here we can see that depending on our platform we will activate the respective controls. This is for touchscreen and this is for the VR. And these controls implement an interface. Let's see, if we go to here, we have these joysticks, and in player avatar we will see we have this throttle movement and the control movement. So the throttle movement is to move the spaceship based on throttle value, which is a scriptable object, just a data container, and the control movement is also a scriptable object that has a vector 3 value. The throttle movement will just take a float value. If it's positive, it will go forward. If it's negative, it will go backward. Control movement will take vector 3 and will create a torque in that direction of the vector 3. These are pretty self-explanatory, and they have no direct dependencies on any of the control script. So it's like a model view control, just a controller and input separation. So we can have any kind of input. The throttle movement and control movement don't need to care where it's getting the value. It will just get the value from the scriptable object. And someone else, which is our input script, will add the values in here. Control handle input will take the value from mobile joystick and will put it in this scriptable object, and same for the throttle handle. And now let's see for the VR. In VR also we have the throttle handle. It also contains the grabbable, grab interactable. These are just Meta's way of doing grabbable things, but it has a calculate throttle input and also a calculate control input. So we will see basically these two main scripts. Let's open them. So for throttle value, we are implementing the iTransformer and iThrottle handle. This is the interface. Made it so that we don't need to be dependent on a single script. Any script that will implement iThrottle handle can be used as a input, as a handle script. But it's not necessary because it's really empty. So for now we really didn't need it, but I added it for later. If I need to make multiple way of controlling the spaceship, then I will have different implementations, but I will implement from this interface, so whatever I write here, it will still work with any script that will reference iThrottle handle. Very simple example of composition. And let's see. So at initialize, we get this axis of rotation of visual transform in the local space, which is whatever we will put in the inspector for here. So here we can see that the x-axis is the axis along which we want to rotate this handle. That's why I took it right. And then in update, we will take the vector from pivot to grabber, and then also the axis of rotation in one space by using transform direction. So it's very simple that the right was the local space. It's 100, but when we transform it to wall space, so it will be calculated based on wall's origin, because the spaceship can be in any orientation, so we don't want that 100 value, which is the local axis of this model or the pivot. We want the uh, walled axis. That's why we transformed the direction, and then we projected it on the plane, and this is how we projected. Axis of rotation in wall space is the normal of the plane. Now so this is the normal, so the plane will be just like this. Yeah, just like this. As I mentioned in the while playing the game, that we will calculate the angle between the grabber and the current grabbable position, and that's what we did, signed angle. And based on the value of the signed angle, we will first clamp it to how much we give a constraint. It's just a scriptable object, so that we set the data once and it stays in all kind of on all the scripts we want. And then once we made it to the once we get the sine angle, then we will just lerp the throttle inputs value between -1 and 1 with an inverse lerp. So first we will inverse lerp, and then we will lerp it. Inverse lerp between the min-max angle constraint, and then we'll lerp it between -1 and 1. Basically, it will just transform this angle within a range of -1 to 1, and then we will just store that value in throttle input, which is our float data scriptable object. So yeah, that's all very simple. And same goes to let's see the control control handle. So there also we have same, but this time we will just choose the vector 3, and here we can see that first we take again the vector from pivot to grabber in wall space, and then we get a projection of x. So this is the pivot transform dot right. So if we go here, and we'll see right, so again the x, we will get the projection vector based on this plane. This is the plane, this will be the plane, and then we will calculate the sine angle as x and also as y, and then we will get a z value, projected z, that will be on the forward direction. So here we are calculating two projected vectors. One is on this plane, and the other is on this plane. One is the plane whose normal is right, another is the plane whose normal is forward. For the right, we are getting the x and y value of the vector, and for the z value we are getting it from the plane whose normal is forward. You can see, and then we are calculating the sine angle, and then we are clamping all the values between the min-max angle constraint, just like how we did in throttle, and then we lerp and inverse lerp. So everyone will be between -1 to 1. So it will be the entire value of this control input will be between -1 to 1. So even in x it will be -1 to 1, in y, in z. So we will basically get a vector which will tell us where how much our hand, which is grabber, is rotating compared to this pivot, and also in which direction. And then we will apply a torque on that vector, which we can see here, control movement, that we just use that vector to add a relative torque. Okay, we use the relative because we want to add that torque based on the spaceship's coordinate system. Yeah, that's very simple as it is. And yeah, that's all for touch screen. We did similar thing. We got the value from the joysticks, which is also between 1 and -1, and then we packed all the values. We took the throttle between -1 and 1, and then we also took the pitch, yaw, and roll between -1 to 1, and then we made a new. You can see we made a new vector 3 and added all the 3 axes into this vector 3 to store the data. And for we also made a MnK. I'm saying we, it is me only. I also made for a mouse and keyboard. We can see it here. I didn't implement it, but it's again same. For mouse and keyboard, I used these new input systems, WSD, QE, which we can surely check it out from here. For throttle, I used left control and space, and for pitch I used S and W. For yaw I used A and D. For roll I used Q and E. And yeah, we added them similarly to the scriptable object, and that's how we made mouse and keyboard, touch screen, as well as VR, all 3 controls for to move the spaceship. So from the values we are getting for from our input, whether it be touchscreen, mobile, or VR Grabbables, we are moving the spaceship. We saw that. Now how about moving the visuals? That's another thing we are doing also same time. So that input and the value we are storing here is not only moving the spaceship but also moving these visuals. And those visual scripts are these: OneAxisRotateTransformer and AllAxisRotateTransformer. We can see it taking the same control input value, reading from it, and then also the angle constraint, and then based on the calculation it's doing, it is moving this visual, and same goes to the throttle handle. It's moving, and here is the sensitivity by which we can say how fast we want this to move. So let's open this and check it out what they actually do. In case of OneAxisRotateTransformer, it's taking the throttle input as a float value between -1 and 1, and then it's simply just calculating in relative angle with sensitivity, inversion, everything calculated, and then it's making a quaternion of that angle, and then it's so this input rotation is in pivot space because this relative angle is in pivot space, and then it's doing the world space rotation by multiplying pivot transform rotation, very simple quaternions, and then it's also doing it's setting this visual transform rotation to the input rotation. And for all axes, again same thing happening, nothing different. Calculating relative x, relative y, relative z, because in there, in case of control handle, we are rotating in all 3 axes, so it's calculating that, and then it's creating an input rotation in pivot space again, and then it's also slurping this time, which is needed because we are here first making the value between 1 and -1, between the negative angle constraint and positive angle constant, and then we are adding it to the local rotation. I think we could have done this way also, just adding it to direct rotation by multiplying with pivot transform.rotation. Here we are not doing that pivot to wall space, that's why we are adding the rotation to local rotation. So yeah, this is it, simple quaternion stuffs.